Hello, and welcome to this webinar on momentum. Today, we're going to talk about what momentum is, of course, conservation of momentum, and a little bit about impulse of a force. So, you probably know the majority of the theory. So, momentum is mass times the velocity. So, it's a vector quantity. So, momentum is mass times velocity. And it's a vector, so P is m times v, or simply just P equals mv, because we don't always have to indicate that we're working with vectors, but we always keep that in mind that it is a vector. So it could be, if it's in one dimension, it could be positive or negative. If it's in two dimensions, then it's just a vector because there's no such thing as a positive vector if you talk about two dimensions, right? It doesn't make any sense. Um, and then impulse is the change in momentum. Some impulse is the change in momentum. Or delta p. So impulse is I, or delta p, and it's the final momentum minus the initial momentum. And of course, it is a vector, right? So normally we work in one dimension, and then we can drop the vector symbols. But yeah, we just keep in mind that the impulse is the change in momentum, and impulse is equal to the force multiplied by the time. So if a force F acts for time t, then the impulse delivered by that force is force times the time. And conservation of momentum, of course, in an isolated system, in the system with no external forces, the total momentum is conserved. So in an isolated system with no external forces, momentum is conserved. So that's conservation of momentum. Lovely. Okay, so let's jump in. I've got some problems of various difficulty, and they are very similar to the ones in the assignment. So I hope you'll find that useful. So hopefully by the end you will know how to solve at least 8 problems from the assignment. Okay, so we have a neutron approaches a nucleus and rebounds directly backwards with the same speed. Right, so we have a neutron that hits a nucleus and rebounds backwards. So it hits the nucleus and rebounds backwards with the same speed. Well, yeah, nobody said it's a stationary nucleus. I think that's the reason, right? Um, I'm just thinking, is that possible at all? Like, because when you hit a stationary wall, yes, you'd bounce back with the same speed. But if you are hitting a movable object, is it at all possible that you bounce back at the same speed? Probably yes. Yes. I can't think a reason why not. But yeah, so it has an initial speed of u equals 6 times 10 to the 6 meters per second. And it rebounds back with v, which is minus 6 times 10 to the 6 meters per second. And the mass of the neutron is 1.7 times 10 to the negative 27 kilograms. And average force. Okay, so an interaction that lasts there. So we know that force is change in momentum divided by the time taken. And change in momentum is the final momentum. So it's mv minus mu divided by the change in the time taken. We can take m out, mass of v minus u divided by delta t. But look, u is actually, well, v is minus u, right? Because they travel, v is minus u. Well, so you can put that in, and that gives 2 mu, minus 2 mu divided by delta t. Oh yeah, lovely. So we can put that in. 2 times mass 1.7 times 10 to the negative 27 kilograms times the velocity, 6 times 10 to the 6 meters per second, and divided by time, which is 2 times 10 to the negative 19, and which is negative 2 times 1.7 times 10 to the negative 27 times, times 10 to the negative 27 times 6 times 10 to the 6 divided by 2 times 10 to the negative 19th, which is minus 0.102 newtons. The negative sign indicates that the force is to the left. So it's not really important. The minus in this particular case doesn't make any difference because, well, yeah, the force is to the left. Of course, the force acting on the neutron is pushing the neutron towards the left. That's why it changes direction. A more interesting thing is that we are talking about an incredibly small particle, the neutron, and yet the force is 0.1 newtons. It's the same force that a 10-gram mass would exert. So you would be able to feel that force. So an unimaginably small particle with an unimaginably small mass hits another particle with such a force that is macroscopic force. We call it a macroscopic force, macroscopic value. So yeah, unless I've made a mistake. Yes, you can write v minus u over t as acceleration, of course. And clicking the 22 webinar links for the past months. Oh, sorry. Sorry for that. Okay, so and that's, I find this fascinating, right? So a very small particle can exert a microscopic particle can exert a macroscopic force. Right. Next one, force from a fluid jet. A water flows steadily through a pipe of cross-sectional area A and exit a nozzle with a volumetric flow rate Q. The jet strikes a vertical wall. Find the speed of the water leaving the nozzle. Find the force on the wall if the water comes to rest on impact. Find the force of the water if the water rebounds straight back with the same speed. Assume the density of water is rho. So what's going on? So we have a vertical wall and we have a water jet. So we have a water jet hitting the wall. So you can assume that it is going horizontally. Of course, it goes in a parabola, but if it goes fast enough, it's barely visible. The bend is barely visible. And it's not really important whether it bends downwards or not, because that has no effect on the horizontal speed. Okay, so cross-sectional area is A, and a volumetric flow rate of Q. So Q is the amount of volume per unit time. But if you have Q is the volumetric flow, so Q is liters per second, right? So Q is cubic meters per second, right? So it's a measure of volume. So Q is volume divided by time. But if you think of this volume, so imagine that this amount of water passes through the pipe, and then this distance is going to be V multiplied by delta T by T. So in time T, the water covers a distance VT. And if you take this cylinder of water inside the pipe, so the volume is equal to A multiplied by VT, volume of water is area, cross-sectional area multiplied by the length, VT. Yes, because for a cylinder, it's cross-sectional area times the length. And then we have the volumetric Q is volume divided by T. So Q is, in fact, AVT divided by T. T cancels out, and we get AV. So the speed of the water is the amount of water divided by the cross-sectional area. And that kind of makes sense. The narrower the cross-sectional area, the faster the water has to flow. You probably know this. If you ever used a garden hose, if you close the if you squeeze the end, the water comes out faster, right? If you make the tube narrower, the water goes faster. So spraying water from a hose. Yeah, so when you do that, right, the water goes faster. And that's the reason why the speed of the water is inversely proportional to the cross-sectional area. It's quite an interesting speed is inversely proportional to a cross-sectional area. That is pretty cool. Anyways, that's the speed of the water. Now, when the mass of the water, so is that question A? Yeah, it is. It is the speed. That's the speed. Mass of the water is, of course, volume times find the force on the wall if the water comes to rest on impact, so B. So in 1 second, sorry, we don't need in 1 second. In time t, the amount of the volume of the water, uh, volume, is equal to A multiplied by VT, right? And yes, oh, isn't that just Q? Well, yeah, it is because AV is just Q. So that's Q times T. That makes perfect sense. The volume. So the mass of the water, mass, M, is density times Q times T. That's the mass of the water hitting the wall in time T. Right. Now, momentum of the water, momentum, is mv, which is rho qt times v, but we know v is q over a, so it's rho qt times q over a, so that's rho q squared t over a. And the change in momentum, of course, the water goes from change of momentum water goes from moving to stationary. So the change in momentum is just minus mv. So it's minus rho q squared to the t. The minus is really not important here. So the force is equal to the change in the momentum divided by the time taken, So minus rho q squared t over a t, t cancels, and we get minus rho q squared over a. That's the force if the water stops. The water hits the wall and stops, and so it basically falls down. Now, see if water rebounds. If water rebounds, then the change in momentum is the final velocity. So that is minus mv, right? Because it goes backwards, changes the velocity. Final velocity is minus mv, initial velocity is mv. So water travels with mv and it bounces back with minus mv. So the change in momentum is minus mv. So final minus initial, which is minus 2 mv. Minus 2 mv, which is minus 2 rho q squared t over a. So it's double. It's double. The force doubles. If the water rebounds back, the force is double the value then when the water stops. Okay. Now, impulse from a time-dependent force. So if you have a force that changes through time, so a force that changes through time and like this, so the impulse is the area under the force time graph. So impulse is the area under the force time graph. Seven B. What do you mean by problem 7B? Isn't it? Let's have a look. Seven B. Well, yeah, you just need to think of what would make the highest speed for one of the particles, right? And then you just well, try different cases, right? So, I mean, if you have three particles, if one particle moves one way and two particles the other way, for example, it would be a higher speed for particle one, something like that. Yeah. Okay, so sorry, that was for problem 7. Right, so a cart of mass 0.4 kilograms moves on a frictionless track. So we have a cart moves on a frictionless track with a speed of 5 meters per second. A force acts on the cart for 2 seconds. Find the impulse delivered to the cart. So we would probably want to sketch that force. And this is time, and this is the force. So let's say that this is 1 second. This is 2 seconds. So 0 to 2. And force, the initial force is 4. So 4. Then after 1 second, the force is 1. So 6, 5. Okay. We can do 1, 2, 3, 4. So the initial force is 0. After 1 second, the force is 5. 5. And after 2 seconds, so that's 4 minus 4. Oh, that doesn't make any sense. 4 plus 8 minus 4. 4 plus 8 minus... That should be 8. That doesn't make any sense. Wait, 4 plus 2 is 6 minus 1, 5. 4 plus... Oh, 4 plus 4 is 8 minus 4, 4. Yes. Sorry. I'm being silly. So yeah, the force acts like this. So it's a parabola. It's an upside down parabola. The maximum force is 5. And yes, so the impulse delivered is the area under the graph. So the area is the integral. Is the integral from 0 to 2 of a 4 plus 2t minus t squared dt. And that's 4t plus 2t squared over 2 minus t cubed over 3 between limits 0 and 2. So we substitute 2, we get 8 plus, so that cancels, 4 minus 8 thirds, which is 12 minus 36 minus 8, 28 thirds, which is 9.33 kilogram meters per second. That's the impulse. That's the impulse delivered. So change in momentum. And then final momentum. Find the impulse delivered to the car. So A, the impulse is the change in momentum. It's the area under the graph, which is 9.33 kilogram meters per second. B, find the cart's speed at 2 seconds if the force acts in the direction of the motion. So the force acts in the same direction. So the final momentum is equal to initial momentum plus the change in momentum plus the impulse. So initial momentum is 5 times 0.4. 5 times 0.4, that's 2, plus 9.33, which is 11.33 kilogram meters per second. And the final velocity is the final momentum divided by the mass. So it's 11.33 divided by 0.4 kilogram meters per second divided by kilograms. Kilograms cancel. We get 11.33 divided by 4. 2.83, 2.8. That doesn't make any sense. We divided 0.4. So that's 28.3 meters per second. Okay. So that's the speed of the trolley after the force has acted. Repeat if the force acts in the opposite direction of motion. Well, then the final momentum is P initial minus delta P, and that's 5 times 0.4 minus 9.33, which is minus 7.33 kilogram meters per second. And the final velocity is minus 7.33 kilogram meters per second divided by 0.4 kilograms, which is 7.33 divided by 0.4, which is negative 18.3 meters per second. So it goes backwards, and I can demonstrate that. So if you take bet motion and forces. So imagine we have an object moving. So let's say masses, values, speed. Um, okay, so the speed of the trolley is 5.4. And imagine I apply a force of 200 newtons for 5 seconds. So, well, I probably won't be able to do that, but just 200 newtons. 1, 2, 3, 4, 5. So you can see that the speed has increased to 34.1 meters per second. Now, if I go back to the okay, 5.2. I can't get to 5.4. Uh, maybe I can do it like this. Okay. It's annoying. 5.4. So the trolley is moving at 5.4 meters a second. And now imagine I apply 200 newtons force, but to the left, right? So I push the trolley to the left for the same 5 seconds. So 1, 2, 3, 4, 5. So now you can see the trolley is moving in the opposite direction with a speed of about 18, right? So I'm roughly in the same ballpark. So first you need to slow down, and then you accelerate. Yes, you can't have speeds too high since there needs to be conservation of energy as well as momentum too. I'm not sure what you're referring to. There's a message about speeds. Maybe when it rebounds at the same with the same speed. Number 4, recoil of a launcher. So a rocket launcher, or more like a cannon, because a rocket usually means it's something self-propelled, but that's not important at the moment. So there's something with an angle of 40 degrees, and it rests on a smooth horizontal surface. So it's a smooth horizontal surface. Smooth. And fires, it has 80 kilograms of mass. It fires a projectile of 4 kilograms, so 4 kilograms, and it fires it at an angle with a speed of 250 meters per second. Find the recoil speed. So the launcher will recoil back. Recoil back at an unknown speed. Let's call that speed v. Oh, actually, you know what? U. I prefer U. U doesn't necessarily mean initial. Okay. So when it shoots the projectile, it will roll backwards effectively. Now, it's interesting because it's not shooting horizontally. So how do we approach that? Well, momentum is conserved in any direction, right? So if you have a momentum conservation, it will be conserved in any direction. Particularly the horizontal momentum is conserved. So momentum will be conserved in any direction. It's conserved in any direction, any chosen, as long as there's no external forces in that direction, right? Because so in this case, there are no horizontal external forces. So horizontal momentum is conserved. Horizontal momentum is conserved. Right. So the you can also think of Newton's third law. So the cannon pushes the projectile, and the projectile pushes the cannon with an equal but opposite force. Okay, so initially the momentum is zero. The total momentum is zero because they're both stationary. And now after launch, momentum of the rocket is the horizontal momentum of the rocket is 4 times 250 times cosine 40 degrees. So that is cosine 40. Oh, that we need degrees. Degrees cos 40. 776. 766 kilogram meters per second. And the launcher must be negative 766 kilogram meters per second. And then the speed of the launcher, okay, velocity. Ah, yikes. Velocity of launcher must be U is the momentum divided by the mass. So it's minus 766 divided by 80 kilogram meters per second. Kilograms cancel. We're left with meters a second. So times 1,000 divided by 80. Negative 9.58 meters per second. So it rebounds at that velocity. But what happens to the vertical momentum? I mean, it has vertical velocity too. So how come is the vertical momentum not conserved? Can somebody tell me? No, you don't have to mention which side you are considering positive. It's as long as it's obvious. F's, well done. Well done. Yes, the vertical component, external force from the normal reaction from the ground. Yes, the normal reaction from the ground is the external force, because when you shoot, the trolley squeezes into the ground, so the normal reaction force increases. So vertically, momentum is not conserved. Vertically, momentum is not conserved. Served as there is normal reaction force. Normal reaction force. It increases when you shoot, so the normal reaction increases, and that's yes. Okay, and that's it. That's all we. That was the answer. That's the speed of the launcher after the recoil. Okay. Inelastic collision between two vehicles. Two carts move along a straight frictionless track. Okay, so and cart A has a mass 300 kilograms. So this is an easy one. Moves at 6 meters per second. Cart B has in the mass 500 kilograms and moves in the opposite direction at unknown speed. So let's call that U. When they collide, a load is transferred. Sorry, a load transfer. That's a silly. How does that work? Okay, there's okay. Let's drop this sentence. It's like what? Doesn't make any sense. Sorry, I didn't see that. When they collide, card B comes to rest, and card A continues at 4 meters a second. So that's A, and that's B. Okay. Uh, so they interact. Okay. So what they mean by the load is that they interact. So they hit each other, but don't hit head on, right? If they hit head on, they can't pass through each other. So they kind of scrape each other, if that makes sense. They scrape each other, perhaps. Oh, I've got an idea. I've got a brilliant idea. So the trolleys don't hit each other head on, but this trolley, so the trolley A, if you look from the top, trolley A has a magnet on top of it. Let's say it has a magnet, and trolley B also has another magnet on top of it. And when they pass each other, they interact. So this is 6 meters a second, and this is U. And then when they pass each other, the magnetic fields interact, and after the collision, A continues to travel in the same direction as 4 meters a second, and B stops. So B stops 0 meters a second. Okay, so hopefully that makes sense because normally they collide, and you can't go through through each other in a collision. Anyways, there's some sort of interaction. It's an interesting thing to think about. An interaction could be anything. It doesn't matter what the interaction is. It could be magnetic. It could be electrostatic. It could be any kind of interaction. It could be a direct collision. But in any interaction, the Newton's third law still applies. So you have uh, action equals reaction. So one A acts on B and B acts on A with this equal but opposite force. Right, so we have conservation of momentum. So m1u1 plus m2u2 must equal to m1v1 plus m2v2. So the initial velocity is 300 times 6 plus 500 times negative u, because it's moving to the left, is equal to m1. So that's 300 times 4 plus 500 times 0. Okay, and we can work out the initial velocity of card B, which is u. So this is minus 500 u is equal to minus 600 minus 600 minus 600. Yeah, so u is 1.2, must be meters per second. So yeah, that's the initial speed. Easy. Okay. Is there no change in mass when load is passed over? Well, no, I'm saying that there's no change. The load hasn't passed over. Well, yeah. So I've dropped that sentence. I don't like that. I don't like that statement. I've just simplified the problem. Okay, an elastic collision with direction change. a puck slides on a frictionless ice. It glides elastically with an ideal puck initially at rest. Identical puck. So we have a puck traveling. It hits an identical puck. After the collision, the first puck moves at an angle of 40 degrees. So after they collide, the first puck moves in this direction. I'll find the speeds. Okay. So we assume we know the initial velocity. So we want to know v1 question mark, and we want to know v2 question mark. Okay. Well, momentum has to be conserved horizontally and vertically. So this, because we know this is 45 degrees, so this is v1 times cos 45, and this is v2 times sine 45. Now this is v2, let's say this angle is theta, we don't know that angle, v2 cos 30 theta, and v2 sine theta. And the masses are identical, so this is m, this is m, this is m, this is m. Right. So first of all, horizontal momentum. Horizontal momentum must be conserved. So mass times u, m times u, must equal to m v1 cos 45 plus m v2 cos theta. M cancels, and you get u must equal to v1 cos 45 plus v2 cos theta. Secondly, um, secondly, vertical momentum. Well, vertical momentum, because initially the puck is moving horizontally, so there's no vertical momentum. So 0 equals v2 sine 45 minus v1 sine 45 minus v2 sine theta. So in other words, v1 sine 45 must equal to v2 sine theta. Okay. That's nice. Can we solve? Can we resolve this? Well, actually, no, we can't, because we have three unknowns. We have three unknowns, which is v1, v2, and theta. These are unknowns. So we need another thing to consider. It says elastically. It's an elastic collision. That means kinetic energy is conserved. And that means that 1/2 mu squared must equal to 1/2 mv1 squared plus 1/2 mv2 squared. So kinetic energy is conserved. So m cancels, 1/2 cancels, and we have u squared equals v1 squared plus v2 squared. How is that helpful? Well, what can I do here? Well, we can try eliminating one of the variables. There's a more elegant solution. And you know what? I'm sure you are really smart people and you can solve three simultaneous equations. So this is equation one, this is equation two, this is equation three. I'm sure you can solve. You can solve for V1, V2, and theta. Okay? So I'm not going to do it algebraically. I'm going to do it. I'm going to do it in an advanced method in a way. Look, momentum is conserved, right? Momentum is conserved, and the total momentum. This is the initial momentum, p0, and after the collision, one of the pucks flies off at p1, and the other puck flies at p2. But we know that the momentum is conserved. That means P0 must equal to P1 plus P2. Or in other words, because these are vectors and we can apply our knowledge of vectors. So this is P0, this is the initial momentum. This is the momentum P1, and this is P2, right? I'm sure you would agree because this is a vector triangle, right? So P1 plus P2 equals P0. But this is a triangle. And from conservation of energy, we've just learned that U squared is V1 squared plus V2 squared. Multiplying both sides by M squared, we get P0 squared equals P1 squared plus P2 squared. And this is a Pythagoras, using Pythagoras theorem, this must be a 90-degree angle. Hence, it is a right angled triangle. In other words, the angle between P1 and P2 must be 90 degrees. And if we know that, that means theta must be 45 degrees as well. And then you can work out V1. Okay, so V1 has to be equal to V2. So V1, the modulus of V1 must equal to the modulus of V2. And therefore, U squared is equal to 2V1 squared. So V1 is U divided by square root of 2. I hope, do you understand that solution? Do you understand that method? So non-algebraic method. Conservation kinetic energy is conserved. Right. Yes, V2 is also V1 over square root of 2. They both have to be like that. Okay, so this one is a really advanced problem. So this is the bag of sand problem. So the sand hits the ground and then slides. Okay, so we have a crate. Well, it doesn't matter if a crate or sand. So basically, we have a rough surface. We have a rough surface with the coefficient of friction mu, and we have a crate that hits the ground at an angle of theta, and it hits the ground and then slides. Okay, hits the ground and slides. At the moment when it hits the ground, the friction increases dramatically. Because it's dynamic. It's because the force of impact is quite large. The sometimes question is what is the condition? What's the minimum coefficient of friction that it stops immediately? So how could it stop immediately? I mean, because the friction force is mu n. Oh, but n is so large because look, when it hits the ground, force of friction is mu n, right? But when the moment it hits the ground, so the normal reaction force, uh, so it's zero. So when it hits the ground, it's huge, it spikes, and then it becomes equal to mg, right? So you can imagine when if you jump from a high surface from a table onto the ground, first your feet, there's lots of force. That's the force that is stopping you, and then it's just mg. So we are this this area up to this point is the change in vertical momentum. Change in vertical momentum. So this is time momentum as a result of collision. Now the problem is we don't know the shape of that graph. We can only estimate some kind of shape, but that's really not important because what we can do is we say that the time is very small and we can assume that this force is constant. So we're going to model this situation is that the force is initially very large and then just drops to zero. Because the force is many times larger than the force of impact is many times larger is of mg. And so the force of impact is many times larger than mg. So we can ignore mg for now because we're only interested in that short time when it hits the ground and then stops or continues sliding. Okay. So it spikes and then just drops to zero. So this is a force of impact. Impact. Okay. So when it hits the ground, there's a huge force from the ground, the normal reaction force. And because that force is much greater than mg, we can ignore the other forces. And that's a very important, that's an important step in this problem. Ignore mg because it's many times less than the normal reaction at impact. All right. So the vertical change in the vertical impulse, it hits the ground and it stops. It's defined, it's the velocity. So it's mv sine theta on the other hand, on one hand. That's the change in vertical momentum because it goes from moving to stop. On the other hand, it's the normal reaction force multiplied by the time it takes to stop. To stop vertically, I mean. The change in horizontal momentum, on the other hand, is the frictional force. So there's a frictional force which is mu n, which is mv cos theta minus well, it keeps sliding, so let's call it v2 v1. So assume create slides at v1 after impact. So you can imagine, yeah, so something hits the ground. So let's say my calculator, so it hits the ground and then keeps moving, right? So, and you're interested in how far it will travel, okay? And yeah, so that's minus, so the change in horizontal momentum is mv cos theta minus m times v1, right? So that's the change, and that's equal to mu n delta t. So it's the frictional force that causes that change in momentum in that very short time delta t, right? The delta t is very short, so mg doesn't have enough time to act in a way. Also, yeah, delta t is very small. Okay, so here we can divide, I guess. We can divide, we can do mv1. Uh, well, we can divide them by each other and divide 2 by 1. 2 divided by 1. What do we get? We get mv cos theta minus mv1 divided by mv sine theta equal to mu. Ooh, lovely. We don't need normal reaction force. We don't need the time of impact. Therefore, we can just work out V1 from here. So mv1 is equal to mv cos theta minus mu mv sine theta. M's cancel, and V1 is V cos theta minus mu sine theta. Oh, that is just beautiful. That's the speed after impact. And we can, how far will it travel? Well, when it hits, after it hit the ground and it's moving it, so it has kinetic energy. So the frictional force that is acting, so when it hits the ground, it's traveling at v1. So once the dynamic force has settled down, so there's a large initial force and then it just becomes mg, right? So after impact, the frictional force, the frictional force is equal to mu mg. Easy, right? Mu mg, and it's moving at a speed v1. So the kinetic energy is 1/2 mv1 squared. That's the kinetic energy after impact, and the work done by friction, its work is force times distance. So distance is the work divided by force, and work energy principle. Yes, kinetic energy is the work done. So in order to stop something, you have to do the amount of work equal to the kinetic energy of the object. So it's 1/2 mv1 squared divided by the frictional force, which is mu mg. Once again, m cancels out, and we get v1 squared divided by 2 mu g, and v1 squared is v squared cos theta minus mu sine theta squared divided by 2 mu g. And we know all of these, so that's the distance traveled after hitting the floor. What is the condition? So B, what is the condition for V1 condition for crate to stop on impact? And that's very easy. That's V1 must equal to 0. Let's look at V1. Oh, V1 and it's equal to V1 is equal to V cos theta minus mu sine theta is 0. So cos theta must equal to mu sine theta. So mu must equal to cot theta? Cot theta, cotangent theta. Oh, that's interesting. Or simply 1 over tan theta. Oh, that's sort of unexpected, but could I have made a mistake? No, I don't think so. Okay. Yep. Cool. Final problem. I think the last one is quite easy. Can we use the vector triangle? Yes, you can use the vector triangle always. It's just it turns out that in this particular triangle, because v1 squared plus v2 squared is equal to u squared, then it's a right angle triangle. So you prove that it's a right angle triangle because you have conservation of energy. If energy was not conserved, it would not be a right angle triangle. And also, if the masses were different, it would not be a right angle. I'm not sure about them. Yeah, if the masses were different, it would be a right angle triangle. Anyways, momentum change in a bounce. A rubber ball of mass charge falls vertically and hits the ground with a speed of 4 meters a second. 4 meters per second. It rebounds vertically upwards and reaches a height of 0.6 meters. Find the change in momentum of the ball due to collision with the floor. Well, we know that it hits the ground at 4 meters a second, so we want to know what's the speed of rebound. So we want to know that v question mark. Well, if it went up by 0.6 meters, we can use just conservation of energy, right? Energy is conserved. So 1/2 mv squared, that's kinetic energy of the ball, turns into gravitational potential energy, so mgh. So m cancels, and you got v squared is equal to 2gh. So v is square root of 2gh. So that's 2 times 10 times h, which is 0.6. This is approximately square root of 2 times 10 times 0.6. That is 3.46 meters per second. So it hits the ground at 4, rebounds at 3.46. So the change in momentum is equal to final momentum, so which is mass times v minus mass times u. And we can say that the initial momentum is 0.15 times 3.46 minus 0.15 times minus 4. We can say that the downwards force is negative 4, and which is 0.15 times 3.46 plus 0.15 times 4, which is 1.12 kilogram meters per second. That's the change in momentum. And if we knew how long it took for the ball to bounce, we could actually find the force. So the force of impact is delta P divided by delta T, but we don't know delta T. So that's the answer. Answer to the question. Right. I hope that was useful. I think I'm going to stop here. I've done 8 questions, went through them quite quickly. I hope you managed to get something out of problem 7. I think problem 7 is the most interesting one. Another thing you can consider is that the change in momentum caused by mg. So mg also is an external force, right? Mg changes of your momentum. But the thing is, because the time is so small, mg barely changes the vertical momentum. And that's what you need to think about here. So because the impact force is so much bigger than mg, you can actually ignore mg, which is probably the hardest part of this question. Because if you don't ignore mg, then the maths becomes just impossibly hard. Okay. Amazing. So Enjoy the rest of your week. Next week, unfortunately, I am unavailable, so I will see you in 2 weeks' time. I will change this the schedule on the website, and so see you all in 2 weeks' time. Bye.